Welcome, AXOR, Galactic Observatory. Tonight, the journey begins at the outer edge of human imagination, where two spacecraft launched in the 1970s continue drifting far beyond the planets, carrying the story of discovery into the dark between the stars. In this documentary, Voyager 1 and Voyager 2 pass the giant worlds of Jupiter-Saturn. Uranus and Neptune cross the invisible boundaries of the heliosphere and reveal astonishing truths about heliopause, interstellar space, magnetic fields and cosmic rays. Their mission is more than exploration. It is a quiet testament to human curiosity, endurance, and the extraordinary reach of science across billions of miles. As the universe slowly unfolds, this story invites wonder, reflection, and a deeper sense of our place in the cosmos. Before we begin, please like the video, subscribe to AXOR, Galactic Observatory, and turn on notifications so you do not miss more journeys into the deep universe. Far beyond the last bright planets, beyond the dim belt of icy bodies that circles in the outer dark, the Sun still carries a kind of territory with it as it moves through the galaxy. This territory is not marked by stone or orbit or any visible wall. It is made instead from flowing particles, magnetic fields, and pressure, and it drifts outward in all directions from the Sun like an expanding breath. Around this moving domain lies another environment, older and larger, the thin material between the stars. It is this larger setting that gives meaning to the long journey of Voyager 1 and Voyager 2, because those spacecraft do not simply travel away from Earth. They move from one cosmic environment into another, from the Sun's local influence toward the wider medium of the Milky Way. The galaxy around the solar system is not empty. It only appears empty because the distances are so large and the matter is so diffuse. In the regions surrounding the Sun, there are atoms, charged particles, dust grains, and magnetic fields spread so thinly that even the best vacuum chambers on Earth are dense by comparison. Most of this material is hydrogen with helium mixed through it, and a small amount of heavier matter. It forms a gentle but persistent environment known as the local interstellar medium. The Sun is moving through this medium at high speed, carrying the planets with it, and from the Sun's point of view, this surrounding material behaves like a headwind. It does not strike the solar system in any dramatic, visible way, yet over vast distances, its pressure matters. It presses on the outer reach of the Sun's influence and helps shape the boundary region that Voyager eventually explores. The solar system then is not resting in stillness. It is traveling. It is embedded in a galactic flow. The Sun orbits the center of the Milky Way over immense spans of time, while also moving relative to nearby clouds of interstellar gas. At present, it appears to lie within or near a local stream of warm, thin material, part of a broader neighborhood, often described as the local interstellar cloud. This cloud is not like a weather cloud with a sharp outline. It is more like a region of slightly enhanced matter in a much larger sea. Its temperature is high by ordinary standards, but because the particles are so sparse, the total heat content is low. In such an environment, a high temperature does not feel like fire. There are too few collisions between particles to transfer much energy. This contrast between high particle speed and low overall density is one of the strange conditions of interstellar space. It is an environment that can be measured but not easily imagined from life on Earth. The magnetic field threaded through this region is also faint, far weaker than Earth's surface field. Yet, over distances of billions of miles, it becomes dynamically important. It can guide charged particles, influence the flow of plasma, and help determine how easily cosmic rays move toward the inner solar system. Cosmic rays are high-energy particles that arrive from violent events across the galaxy, including exploding stars and other energetic sources. The Sun's outward flow helps shield the planets from some of them, but beyond that shield, their intensity rises. This means that the outer setting of the Voyager story is not only quiet distance, it is also a physical environment with pressure motion magnetism and radiation. Before any spacecraft could sample it, directly scientists had to infer its properties from distant observations of starlight radio emissions and theoretical models. They could study how light changed as it passed through gas or map the signal from hydrogen spread across space, but direct measurement remained out of reach. The stars were visible, yet the medium between them remained more abstract, more mathematical than tangible. Voyager changes that condition slowly, year by year, not by racing toward another star, but by continuing outward long enough to meet the edge of the Sun's domain. To understand why that edge exists at all, it helps to begin with the difference between the Sun and the space around it. A star does not merely shine. It also releases a continuous outward stream of charged particles. That stream expands into the surrounding galaxy and pushes against the interstellar medium. As long as the outward pressure remains stronger than the pressure from outside, the Sun maintains a cavity around itself. That cavity contains the planets and extends far beyond them. It is not empty inside, and it is not empty outside. It is a contest between two very thin plasmas, both almost ghostly, yet both real enough to create boundaries. From far away, the solar system might be imagined as traveling inside a moving bubble, compressed at the front and drawn out behind, though the true shape turns out to be more complex than early models suggest. Even so, the basic picture remains useful. The Sun inflates a region around itself, and the galaxy presses back. Voyager begins deep inside that inflated region, near a small rocky world, orbiting an ordinary star in one spiral arm of the Milky Way. But the full meaning of its journey becomes clear only when set against this outer backdrop. The spacecraft are launched from Earth during a rare planetary alignment, yet the deepest scientific value of their mission emerges much later when the giant planets are behind them and almost all familiar landmarks are gone. At that stage, the surrounding darkness is no longer merely distance. It is structure. It contains a boundary between stellar influence and galactic environment, between the solar wind and the medium between stars. The region ahead is so rarefied that a cubic meter holds only a tiny whisper of matter compared with air at sea level, and yet even that whisper is enough to oppose the Sun across immense scales. The setting is quiet but not still. The pressure is tiny but not negligible. The magnetic field is weak but not irrelevant. Every part of this outer environment shapes the frontier toward which Voyager drifts. In that sense, the mission begins not at launch, and not even at Jupiter or Saturn, but here in the broad galactic context, where the solar system reveals itself as a moving island inside a larger cosmic sea. The Sun's surrounding bubble begins with something that cannot be seen directly by ordinary sight, though its effects reach every planet. From the outer layer of the Sun's atmosphere, a steady stream of charged particles flows outward in all directions. This stream is called the solar wind, though it is not wind in the earthly sense. It is a plasma, a state of matter in which electrons and atomic nuclei move freely rather than remaining bound together. The solar wind carries not only particles, but also part of the Sun's magnetic field stretched outward and twisted by the Sun's rotation into a broad spiral pattern. Near Earth, this flow is already thin, but it still has enough force to buffet magnetic fields, shape planetary space environments, and trigger auroras when it interacts with a world like Earth that possesses a magnetic shield. Farther out, the same stream continues across the giant distances of the outer solar system. It weakens as it spreads, but it does not vanish. It keeps moving outward, carrying solar influence deep into the dark. In doing so, it creates the great cavity around the Sun that gives the Voyager mission its final scientific setting. This cavity is known as the heliosphere. It can be imagined as the full region dominated by the outward pressure of the solar wind and by the magnetic field carried within that flow. All of the planets orbit inside it. So do comets on long paths and small icy bodies at the edge of the Sun's family. Yet the heliosphere is much larger than the orbital architecture usually shown in pictures of the solar system. It extends far beyond Neptune, far beyond the region where sunlight still gives a weak but familiar illumination. Its outer structure is invisible in ordinary light because it is not built from solid surfaces or glowing gas. It is a boundary system produced by pressure balance, magnetic tension, and the motion of plasma. The heliosphere exists because the Sun is active in a physical sense, constantly releasing material into space. If the Sun merely shone without expelling particles, then the planets would still receive light and heat, but there would be no great solar bubble of the kind Voyager eventually measures. The solar wind moves much faster than the speed of sound in the plasma conditions close to the Sun, which means it initially expands in a supersonic state. As long as it remains strong enough, it pushes the surrounding interstellar medium aside. This creates a zone in which solar material dominates. Within that zone, the properties of plasma magnetic field and energetic particles are largely determined by the Sun rather than by the galaxy outside. The result is not a rigid shell, but a dynamic breathing structure. The solar wind changes with the Sun's activity. Over roughly 11-year cycles, solar eruptions and magnetic reorganizations alter the strength and texture of the outflow. Fast and slow streams move through one another. Shock fronts can travel outward from powerful solar events. These changes propagate across the heliosphere over long periods, meaning that the distant boundary sampled by Voyager is never perfectly fixed. It shifts and responds, sometimes gradually, sometimes more abruptly, to changes that began far closer to the Sun. Inside the heliosphere, planetary magnetic environments exist like smaller islands within a larger sea. Earth's magnetosphere, Jupiter's vast magnetic domain, and the induced magnetic envelopes around some other worlds all occupy local regions, but they remain embedded within the wider solar wind. This makes the heliosphere the largest coherent structure produced by the Sun, a kind of extended atmosphere on a scale so vast that even light takes many hours to cross significant portions of it. Yet despite its scale, it remains delicate. The density of the solar wind falls with distance because the same outflow must spread across an ever larger area. This decline means that eventually the outward push becomes weak enough for the surrounding interstellar medium to matter more strongly. There is no sudden hard wall at first. Instead, the heliosphere has layers and transitions. Scientists once pictured it in simpler form, perhaps like a comet shape with a rounded front and a long trailing tail. That image still offers a useful starting point, since the Sun's motion through the galaxy does create asymmetry. The front side, facing into the interstellar flow, is expected to feel stronger compression. The trailing side is expected to stretch farther. But as measurements and models improve, the true structure appears more complicated. Magnetic fields can alter the shape. Time variability from the Sun can wrinkle or distort the outer regions. Different particles trace different aspects of the boundary. What remains consistent is the central principle. The heliosphere is a protective cavity formed by the outward solar wind in a surrounding galactic medium. That protection is not complete, but it is significant. One of its most important effects involves cosmic rays, the high-energy particles that travel through the galaxy. The heliosphere reduces the number that penetrate to the inner solar system, especially the lower energy portion of that population. This shielding helps shape the radiation environment experienced by planets and spacecraft. As Voyager travels outward, one of the clearest signs of approaching the edge is a change in those particle populations. Inward of the outer boundary, the Sun still exerts control. Beyond it, galactic influence becomes stronger. The heliosphere therefore matters not only as a geometric volume, but as a filter and mediator between local stellar activity and the broader conditions of interstellar space. It is the Sun's largest physical relationship with its surroundings. In human terms, it transforms the solar system from a simple family of orbiting worlds into a moving plasma structure embedded in the galaxy. The planets circle the Sun, but the entire system together also interacts with what lies beyond. This is the environment that Voyager gradually approaches after leaving the familiar planetary realm. The spacecraft do not fly toward a visible borderline. They cross changes in pressure, particle intensity, and magnetic behavior. The heliosphere is the reason those changes exist. It is the Sun's bubble inflated by an endless outward wind, shaped by motion, weakened by distance, and pressed on all sides by the thin but persistent medium between the stars. Long before Voyager reaches its edge, the logic of the mission is already set by this invisible structure. The spacecraft are not simply traveling far. They are moving through the layered architecture of the Sun's extended presence, from the strong interior influence of a living star toward the place where that influence finally begins to yield. The path that carries Voyager 1 and Voyager 2 toward the edge of the heliosphere begins with an opportunity so rare that it shapes an entire era of exploration. In the outer solar system, the giant planets do not remain in useful alignment very often. Jupiter, Saturn, Uranus and Neptune move slowly in broad orbits, each taking many years to circle the Sun. Most of the time, they are arranged in ways that would require separate missions, separate launch windows, and far greater fuel to reach one after another. But in the middle of the 20th century, mission planners recognize that a special configuration is approaching, one in which a spacecraft can use the gravity of one giant planet to bend its path and gain speed toward the next. This method, known as a gravity assist, depends on motion as much as mass. A spacecraft falls into the moving gravitational field of a planet and departs with a changed trajectory and greater energy relative to the Sun. The planet loses a tiny amount of orbital energy, in return far too small to notice in its motion, while the spacecraft gains a decisive advantage. In the late 1960s and early 1970s, scientists and engineers understand that such a chain of encounters will soon become possible across the outer planets. It is not a yearly chance, nor even a chance that returns within a normal career. It is a planetary rhythm measured across many lifetimes. From this recognition emerges the basic concept that eventually becomes the Voyager mission. Early studies imagine a grand tour of the outer planets, using the rare alignment to send robotic explorers from one world to the next. Budget limits, technical realities and political choices reshape those early ambitions, but the core idea survives. Two spacecraft are built, not one, so that the mission has resilience, broader scientific reach, and the possibility of diverging paths after the first planetary encounters. Voyager. 2 launches first followed shortly by Voyager 1, though the numbering reflects planned arrival order rather than launch sequence. Their departures take place in 1977, at a moment when celestial mechanics, engineering readiness, and scientific ambition briefly meet. The launch itself is dramatic in human terms, but the deeper story lies in the geometry. The planets are arranged so that Jupiter can fling a spacecraft onward, Saturn can redirect it again, and for one of the 2 probes, the path can continue to Uranus and Neptune. Without this alignment, the outer planets would remain vastly more difficult to reach in a single mission architecture. The Grand Tour is therefore not simply a route. It is a temporary opening in the structure of the solar system. It allows machines built by one generation to gather data from regions that would otherwise demand multiple generations of effort. The planners who shape the mission are working with limited computing power by modern standards, yet their understanding of orbital mechanics is exact enough to place the spacecraft on paths that unfold over decades. They know the planets will not wait. Launch too early or too late, and the elegant chain of encounters begins to fail. This adds urgency to the program. The spacecraft must be ready, the rockets must perform, and the instruments must survive long enough to transform a mathematical possibility into an actual crossing of worlds. The Grand Tour concept also changes the scientific meaning of the mission. Instead of treating each giant planet as an isolated destination, the mission links them in a comparative sequence. Jupiter, Saturn, Uranus and Neptune become chapters in one outward movement, each encounter informing the next. The outer solar system begins to appear not as scattered points of interest, but as a connected realm with patterns, contrasts, and shared histories. Even before launch, the mission embodies a shift in perspective. It treats deep space travel as a matter of precision and patience rather than sheer force. It relies on the natural motion of planets, on timing, more than power. This is one reason the Voyager story feels so large. It is not only about what the spacecraft find. It is also about how human knowledge learns to ride the structure of the solar system itself. The 2 vehicles are sent outward with instruments for imaging, particle detection, magnetic measurement, radio science, and plasma study. Yet none of those tools would matter in the same way without the route that carries them. The rare alignment gives the mission both reach and destiny. Voyager 1 is directed toward Jupiter and Saturn with a path that includes the moon Titan as a major priority, because Titan's thick atmosphere holds exceptional scientific promise. That choice eventually bends Voyager 1 above the plane of the planets and ends its chance to continue to Uranus and Neptune, but it also places it on a faster route toward the outer boundary of the heliosphere. Voyager 2, by contrast, remains on the longer arc, continuing after Saturn to Uranus and then Neptune. Together, the 2 spacecraft divide the grand opportunity between them. One becomes the first to move toward interstellar space. The other completes the fuller planetary sweep. This division is not an accident, but an elegant adaptation of limited means to vast objectives. The mission's origin therefore contains both ambition and compromise, both openness and restraint. It begins because the planets line up, but it succeeds because engineers and scientists know how to translate that alignment into action. The Grand Tour is a gift of celestial timing, yet it becomes real only through human calculation, restraint, and persistence. In this way, the outward journey of Voyager does not begin in the distant dark. It begins in a moment when the architecture of the solar system briefly offers a path, and human beings recognize it, measure it, and choose to follow. To cross the giant distances between the planets and continue far beyond them, Voyager 1 and Voyager 2 require a form of endurance that is easy to underestimate from the vantage point of later decades. They are built in the 1970s in an era of modest memory-limited processing power and electronics that by later standards appear almost austere. Yet this very restraint becomes part of their strength. The spacecraft are designed not as delicate laboratories for short display, but as compact, resilient systems meant to function in cold darkness radiation and isolation for far longer than their original planetary phase might suggest. Each craft carries a large dish antenna for communication with Earth, a set of scientific instruments mounted in careful arrangement, small thrusters for attitude control, onboard computers for command and data handling, and a power source able to operate far from the Sun, where solar panels would become ineffective. The overall shape is functional rather than elegant in any ornamental sense. It is the geometry of necessity, a structure in which every component must justify its mass, its energy use, and its reliability. One of the central reasons Voyager survives so long is that it does not depend on sunlight for electrical power. Instead, each spacecraft uses radioisotope thermoelectric generators, often shortened in speech to RTGs, though the idea itself is straightforward. A radioactive material slowly decays and releases heat. That heat is converted into electricity through solid-state devices with no moving mechanical parts. This method is not highly efficient, but it is steady and dependable. In the outer solar system, where sunlight fades to a weak gleam, such steadiness matters more than efficiency. The power output declines gradually over time as the radioactive source weakens, yet it does so slowly enough to support decades of operation. This gradual decline becomes one of the long-term constraints of the mission. Engineers must eventually decide which instruments can remain on and which must be shut down to conserve energy. But the very fact that such choices arise after so many years is itself a sign of extraordinary design. The computers aboard Voyager are similarly modest in raw capability, yet they are arranged with care. Separate systems handle command processing flight control and the packaging of scientific data. Their memory is tiny by modern comparison, but the spacecraft are not asked to do what later machines do. They are built for focused tasks, for repeated logic, for dependable execution, rather than elaborate autonomy. Commands sent from Earth can take many hours to arrive when the spacecraft are far away, so the onboard systems must maintain orientation, follow timing sequences, and protect basic operations, even when direct human intervention is impossible in the moment. This is not intelligence in a modern conversational sense. It is disciplined autonomy, the kind that comes from engineering clarity. The spacecraft know how to keep themselves pointed, how to store and relay data, and how to continue through long intervals of silence. Their communication system is another part of this endurance. The high-gain antenna, broad and dish-shaped, sends faint radio signals back to Earth across unimaginable distances. Over time, those signals become so weak that receiving them requires the immense dishes of the Deep Space Network, a global system of antennas spaced around the planet, so that at least one can listen as Earth rotates. The signal power arriving at Earth eventually becomes almost vanishingly small, far below the level of ordinary background disturbances, Yet, with careful processing, it remains detectable. This is one of the quiet wonders of the mission. A machine built when memory is measured on a tiny scale continues to whisper across billions of miles, and Earth continues to hear it. That achievement depends not only on the spacecraft, but on the patient refinement of ground systems, error correction methods, and communication strategies over many decades. Voyager's instruments are also chosen with a balance of breadth and durability. Cameras reveal the planets and their moons during the encounter years. Magnetometers trace invisible fields. Plasma instruments examine charged particles in flowing space environments. Cosmic ray detectors and low-energy particle instruments measure radiation populations that become especially important near the edge of the heliosphere. Radio science experiments use the spacecraft's transmissions to probe atmospheres and rings. Not every instrument remains useful in every phase of the mission, and not every subsystem lasts forever. Some components degrade, some fail, and some become less central as the spacecraft move beyond the planetary realm. Yet enough remain functional for the mission to transform itself from a tour of giant planets into a long study of the outer heliosphere and interstellar space. This capacity for transformation is one of Voyager's deepest engineering strengths. The spacecraft are not rebuilt in flight, but they are continually reinterpreted. The same hardware that once studies Jupiter's environment later helps reveal the character of the boundary between solar and interstellar plasma. Reliability on this scale also depends on thermal control, mechanical stability, and careful fuel use. The spacecraft must maintain suitable temperatures despite the growing cold of deep space. They must fire small thrusters to keep the antenna pointed toward Earth and the instruments correctly aligned, but every such correction consumes finite propellant. Over time, mission teams refine sequences to preserve what remains. This creates a strange partnership across generations. Engineers who were not alive at launch later help sustain machines older than many of the people communicating with them. They study aging behavior, invent workarounds, and send commands that feel almost like acts of care. Errors do occur. Memory bits can flip. Instrument settings can drift. Yet again and again, the spacecraft prove recoverable, not because they are indestructible, but because they are understandable. Their architecture is simple enough, disciplined enough, that skilled teams can reason through failure and restore function. In this way, Voyager embodies a particular kind of technological wisdom. It does not depend on abundance. It depends on clarity, redundancy, patience, and restraint. Built with the tools of the 1970s, it continues to operate not by miracle alone, but by the lasting power of well-chosen design. Long after the planned planetary encounters end, the spacecraft endure as working instruments in the dark, still powered by fading nuclear heat, still turned toward Earth, still carrying their small persistent ability to measure and to speak. Jupiter is the first giant threshold in the outward passage of Voyager, and when the spacecraft approaches it, the mission moves from careful preparation into direct revelation. Before this encounter, Jupiter is already known as the largest planet in the solar system, a world of belt zones, storms, and powerful radiation. Telescopes on Earth have shown its changing cloud bands and the persistent oval of the Great Red Spot, while earlier probes have supplied important measurements of its environment. Yet much remains unresolved. The scale of the Jovian system, with its retinue of moons, its immense magnetic field, and its fast rotation, suggests that Jupiter is almost a solar system in miniature. Voyager brings the first sustained close view of that system, and in doing so, it changes the scientific imagination of the outer planets. As the spacecraft nears Jupiter, the planet grows from a bright object into a structured world of moving atmosphere and energetic space. Its cloud tops are not still surfaces, but layered currents shaped by heat rising from below and by the rapid turning of the planet itself. Jupiter rotates in less than half an Earth day, and that speed stretches its weather into long parallel bands. Between those bands, storms develop, merge, and dissolve. The Great Red Spot, already famous from distant observations, appears not as a simple mark, but as a vast atmospheric vortex large enough to contain Earth several times over. Around it, smaller storms swirl like eddies in a larger stream. Voyager's cameras reveal motion, texture, and contrast on a level never seen before. The atmosphere looks restless and deeply active, a place where energy is continuously redistributed through towering clouds and layered circulation. These images matter not only because they are beautiful, but because they reveal that the giant planets are not inert balls of gas. They are dynamic meteorological worlds governed by physics that connects fluid motion, chemistry, sunlight, and internal heat. Jupiter gives off more energy than it receives from the Sun, which means its atmosphere is driven not only by external illumination, but by heat still escaping from within. This helps explain why its weather is so vigorous despite its great distance from the Sun. Yet the visible clouds are only part of the Jovian story. Around the planet extends a magnetic environment of astonishing scale. Jupiter's magnetic field is far stronger than Earth's and encloses a vast magnetosphere, a region where charged particles are trapped, accelerated, and guided by invisible lines of force. This environment is dangerous to electronics and revealing to science. It shows that Jupiter is not merely a planet with weather, it is also an engine of plasma and radiation. Voyager measures this environment, directly tracing the behavior of energetic particles and fields. The results confirm that Jupiter dominates surrounding space on a scale far beyond its visible disk. Some of the charged material within this region is linked to the volcanic moon Io, which turns out to be one of the most startling discoveries of the entire mission. Before Voyager, active volcanism beyond Earth is not established in this form. The moons of the outer planets are often imagined as cold and geologically quiet. But Io overturns that assumption. Voyager images reveal plumes rising above its surface, evidence of ongoing volcanic eruption. This is not ancient frozen geology. It is present activity driven by tidal heating, as Jupiter's immense gravity flexes the moon's interior. The discovery is profound because it shows that distance from the Sun does not guarantee geological stillness. A body can remain active through internal energy generated by orbital stress. With Io, the outer solar system becomes suddenly more varied and more alive in a geological sense than many had expected. Europa, Ganymede, and Callisto also emerge as worlds of character, rather than featureless points. Europa shows a surface of ice marked by lines and fractures hinting at processes beneath. Ganymede appears large and complex, with mixed terrains suggesting long internal history. Callisto preserves older scars and darker landscapes. Together, the Galilean moons transform the understanding of what a planetary system can contain. Around one giant planet, there exist multiple worlds, each following different physical paths. The diversity is almost planetary in its own right. Jupiter's ring system, though faint, also comes into view. This is another important correction to earlier expectations. Rings are not unique to Saturn. They can form around other giant planets as well, though with different brightness and structure. The idea of the outer planets begins to shift from a set of isolated curiosities into a family of related but distinct systems, each containing atmospheres, magnetic fields, rings, and complex moons. Jupiter becomes the first proof of this broader pattern. The gravity assist at Jupiter is as important to the mission's path as the science is to its legacy. As Voyager passes through the Jovian system, the planet's gravity bends the spacecraft's route and increases its speed relative to the Sun. This maneuver is not visible like a rocket burn, yet it is one of the crucial acts of the Grand Tour. Jupiter does not simply reveal itself, it also throws the spacecraft onward. In this sense, the encounter combines knowledge and motion. The planet is both destination and instrument. It grants data while shaping the future of the voyage. The emotional scale of the encounter comes partly from this dual role. Jupiter is the first giant world, the first dramatic test of the mission, and the first step in a much longer outward transition. After Voyager leaves, the images and measurements remain, and they alter the scientific picture permanently. The giant planets are no longer remote lights with broad categories attached to them. They are active systems, each with hidden complexity. Jupiter, in particular, emerges as a world of atmospheric turbulence, magnetic power, faint rings, and moons that behave as full physical worlds. The outward road of Voyager becomes real here. It is at Jupiter that the spacecraft proves it can survive, measure, transmit, and continue. The first giant realm opens, and the solar system becomes larger, stranger, and more detailed than it had seemed before. After Jupiter, the path of Voyager leads onward to Saturn, a world long known for its rings and for the quiet elegance it presents through telescopes. From Earth, Saturn appears less turbulent than Jupiter, more restrained in color, its beauty shaped by distance and by the broad architecture of the ring system around it. Yet as Voyager approaches, the calm impression begins to unfold into a more layered reality. Saturn is not merely a planet with rings attached. It is a system of atmosphere, magnetism moons, and orbiting debris, all linked through gravity and motion. The encounter becomes one of the defining passages of the mission, not only because Saturn itself proves rich with detail, but because one of its moons, Titan, carries such scientific weight that it changes the future course of Voyager 1. The planet's visible atmosphere is banded like Jupiter's, though generally softer in contrast. Its clouds appear more subdued, partly because the upper haze smooths some of the visual texture. Even so, Voyager reveals structure within that apparent gentleness. Winds sweep across the planet at high speed, and broad weather systems move through the upper layers. Saturn, like Jupiter, radiates more energy than it receives from the Sun, showing that internal heat continues to shape its atmospheric behavior. The fast rotation of the planet stretches cloud patterns into parallel bands, and the flattened shape at the poles and equator reflects the effect of that rapid spin. Saturn is less dense than any other planet, composed largely of hydrogen and helium, but its low average density does not mean simplicity. Beneath the visible clouds lies deep pressure-changing chemistry and an interior that supports a magnetic field extending far into surrounding space. Voyager measures that field and confirms that Saturn too possesses a large magnetosphere, though different in scale and structure from Jupiter's. Charged particles move through this environment, guided by invisible lines of force, and the rings and moons participate in ways that make the whole region feel interconnected rather than separate. The rings themselves become one of the great visual and scientific achievements of the encounter. From afar, they seem like broad continuous bands, but Voyager shows that they are divided into countless narrower structures, ringlets, gaps, waves, and braided patterns. Some of these features are shaped by the gravitational influence of moons orbiting nearby or within the ring system. These small companions act as shepherds, helping maintain sharp edges or creating disturbances through repeated orbital interaction. The rings are not solid sheets. They are made of innumerable particles, mostly ice, with some darker material, each following its own path around the planet. Seen together, those particles form an ordered yet changing system, delicate in appearance, but governed by strict gravitational rules. Light reflects from them with a pale brilliance that makes Saturn visually unlike any other planet, but the deeper significance lies in what they reveal about disk dynamics. In the rings, scientists can observe processes that echo larger structures elsewhere in the universe, including the behavior of matter in rotating disks around stars and perhaps in early planetary systems. Saturn's moons add further complexity. Some are small and irregular, others are larger and geologically more suggestive. Yet among them all, Titan stands apart. Even before Voyager arrives, Titan draws attention because it is known to possess a thick atmosphere unusual for a moon. Most moons are airless, or nearly so. Titan is different. It is wrapped in an opaque orange haze that hides the surface from view. This alone makes it compelling. A moon with a dense atmosphere invites questions about chemistry, climate, and the possibility of processes that in some distant way resemble those of early Earth, though under much colder conditions. Voyager's instruments cannot see directly through Titan's haze to the ground, but they measure the atmosphere and establish important facts about its composition and structure. Nitrogen dominates, making Titan unique among moons in the solar system. Methane is also present, along with more complex chemistry generated high in the atmosphere by sunlight and energetic particles. These findings deepen the sense that Titan is not just another satellite orbiting a giant planet. It is a world with layers, weather, and chemical pathways of its own. The scientific priority of Titan is so great that Voyager 1 is directed onto a trajectory that passes close to it. This decision comes with consequence. To make the close encounter, Voyager 1 must leave the plane in which the planets roughly orbit. Once that happens, it can no longer continue onward to Uranus and Neptune. The spacecraft will instead head on a steeper path out of the planetary realm and toward the outer heliosphere. This makes Saturn a turning point not only in space, but in mission identity. At Saturn, Voyager 1 chooses depth of study over continuation of the full planetary chain. Voyager 2 will later continue to the more distant ice giants, but Voyager 1 becomes the earlier pathfinder toward interstellar space because of this choice. Titan therefore alters history through a scientific decision rooted in curiosity about an unseen surface and a remarkable atmosphere. Saturn's system also reveals the gentle but constant work of orbital resonance, ring shaping, and moon interaction. The more closely Voyager looks, the less static the planet appears. Features that once seemed decorative become dynamic. The rings hold waves and wakes. Moons influence one another. Fields and particles circulate through near-invisible structures. Even the seeming quiet of Saturn contains motion on every scale. The encounter broadens the lesson first learned at Jupiter. Giant planets are not simple masses with minor attendants. They are whole systems, each organized in its own way. Yet Saturn adds another layer to that lesson through Titan, because here, the most scientifically provocative object is not the planet alone, but a moon concealed beneath haze. In that concealed world lies a future that later missions will continue to explore. But for Voyager, the meaning is already clear. Saturn is both revelation and divergence. It opens the ringed planet in all its subtle complexity, and at the same time, it redirects one spacecraft toward the long outer frontier. From here onward, the mission begins to separate into two destinies, one turning more quickly toward the dark edge of the Sun's domain, the other carrying the grand tour deeper into the cold. Beyond Saturn, the path of Voyager 2 enters a region of the solar system that for most of human history exists more as calculation than as experience. Uranus has been known since the 18th century, but knowledge of it remains thin for a very long time. Through telescopes, it appears as a small pale disk, distant and quiet a planet without the rich visible drama of Jupiter or the striking ring brightness of Saturn. Its remoteness makes it difficult to study from Earth, and before Voyager 2 arrives, much about it remains uncertain in detail. Yet the encounter reveals that Uranus is not empty of character. It is instead a world of subtle oddity, one whose most important qualities are not immediately obvious to the eye. As Voyager approaches, Uranus emerges as a planet defined by unusual geometry, faint structures, and hidden internal questions. Its blue-green color comes from methane in the atmosphere, which absorbs red light and leaves shorter wavelengths more strongly reflected. The result is calm in appearance, but that calm can be misleading. Uranus is an ice giant different in composition and structure from the larger gas giants Jupiter and Saturn. Hydrogen and helium are still present, yet a greater fraction of heavier volatile substances, including water ammonia and methane, is thought to exist within its deeper interior. In planetary science, these substances are called ices, not because they are literally frozen in the usual sense throughout the planet, but because they belong to a class of materials that condense at relatively low temperatures. Under the immense pressures inside Uranus, they may exist in exotic fluid states, unlike anything familiar on Earth. This means that Uranus is not simply a smaller version of Jupiter. It represents another planetary category, one that broadens the architecture of the solar system. The most striking fact about Uranus is its tilt. The planet's rotational axis lies tipped by about a right angle compared with the plane of its orbit, so that it seems almost to roll around the Sun, rather than spin upright like most other planets. This creates seasons of extreme length and peculiarity. For long spans, one pole points more directly toward the Sun, while the other remains turned away, and then, over decades, the lighting geometry slowly changes. The effect is so unusual that Uranus seems less like a standard spinning globe and more like a world reoriented by some deep event in its past. Scientists have long considered whether a giant collision early in the planet's history might explain this remarkable tilt, though the exact origin remains uncertain. Voyager does not solve that ancient question directly, but by revealing the planet's present structure, it gives the problem greater definition. The atmosphere appears smoother than those of Jupiter and Saturn, with less obvious banding in visible light, yet measurements show that motion is still present. Winds move through the upper layers, and the seeming stillness reflects observational limits and haze as much as true inactivity. The deeper atmosphere remains largely concealed, leaving Uranus with an air of reserve, as though much of its nature is hidden below a pale outer veil. If the planet itself is unusual, its magnetic field is perhaps even more surprising. Planetary magnetic fields are often expected to align roughly with rotational axes and to be centered near the planetary core. Uranus does not behave so neatly. Voyager finds that its magnetic field is both strongly tilted relative to the rotation axis and significantly offset from the planet's center. This creates a magnetosphere of asymmetrical and changing geometry, one that swings through space in a way unlike the more familiar cases of Earth or even Jupiter. The discovery matters because magnetic fields are clues to internal structure and to the motion of electrically conducting material within a planet. Uranus suggests that the processes generating such fields can occur in different regions or under different conditions than earlier simple models assume. Again, the lesson of Voyager grows broader. The planets are not variations on a single pattern. They are distinct physical experiments shaped by different histories. Voyager also confirms that Uranus possesses rings, though they are dark and much less visually prominent than Saturn's. Their existence helps establish that ring systems are a common feature among giant planets, but the differences between them are as instructive as the similarities. Uranus's rings are narrow, dim, and more difficult to detect, composed of material that reflects less light. Their subdued appearance fits the general character of the Uranian system, where many of the most important facts are structural rather than spectacular. The moons, too, contribute to this sense of muted complexity. Voyager observes several known satellites in greater detail and discovers additional small moons. Miranda becomes one of the most arresting objects in the encounter. Its surface appears broken into contrasting terrains, with giant cliffs, ridges, and regions that seem almost patched together from different geological histories. It looks less like a uniformly aged moon and more like a body that has undergone disruption, reassembly, or intense internal reshaping. Other moons show their own mixture of craters, fractures, and ancient surfaces. None of them carries the obvious volcanic shock of Io or the atmospheric mystery of Titan. Yet together, they reveal that the Uranian system has a long and varied history recorded in ice and rock. The farther Voyager goes, the clearer it becomes that distance from the Sun does not reduce complexity. It simply changes the form complexity takes. Uranus's dim light and pale colors conceal a planet of radical tilt, unusual magnetism, narrow rings, and strangely marked moons. The encounter also marks a psychological shift in the outward voyage. With Uranus, Voyager 2 has passed beyond the worlds, long known in detail through ordinary telescopic familiarity, and entered a region that remains almost untouched before the spacecraft arrives. The solar system feels larger again, less settled, less fully claimed by prior knowledge. Uranus is not the dramatic climax of the planetary tour, but it is a deepening of it. It shows that the outer cold can hold not emptiness, but originality. A planet can appear quiet and still overturn expectation through the angle of its spin, the shape of its magnetic field, and the broken landscapes of its moons. In the pale light around Uranus, Voyager finds not grandeur in the obvious sense, but strangeness of structure, and that strangeness expands the map of what a planetary world can be. After Uranus, the outward route of Voyager 2 reaches its final planetary destination, and with it, the last giant world ever visited at close range by a spacecraft from Earth. Neptune lies so far from the Sun that for most of human history it exists as a mathematical consequence before it becomes an observed planet. Its discovery in the 19th century follows from subtle irregularities in the motion of Uranus, showing that gravity can reveal a hidden world before the eye confirms it. Even after that discovery, Neptune remains remote in both distance and understanding. Through telescopes, it appears as a small blue disk colder and dimmer than the planets visited earlier, and its great separation from the Sun suggests a place where activity might be weak and change might be slow. Yet when Voyager 2 arrives, Neptune overturns that expectation with quiet force. It proves to be a world of motion, weather, and internal energy, and its largest moon. Triton reveals a frozen landscape that is not geologically dead. The encounter becomes the last major chapter of the planetary grand tour, but it does not feel like a fading end. It feels instead like a final widening of the outer solar system's complexity. Neptune's deep blue color arises largely from methane in the atmosphere, which absorbs red wavelengths of sunlight. Though the exact richness of the color may also reflect atmospheric structure and composition, not yet fully explained by simple models. What is immediately striking is that despite the weak sunlight at Neptune's great distance, the atmosphere is active. Voyager images show bright clouds and darker large-scale features moving through the upper layers. Among these is a broad storm system that becomes known as the Great Dark Spot, an atmospheric vortex reminiscent in some respects of storms seen on other giant planets, though not identical in behavior or permanence. The presence of such features is important because it shows that solar heating alone does not govern outer planetary weather. Neptune, like the other giant planets, emits more energy than it receives from the Sun. Internal heat continues to escape from the planet's depths, helping drive atmospheric circulation even in a region where sunlight is sparse and weak. Winds measured, there are among the fastest known in the solar system. This fact is almost counterintuitive. Far from the Sun in cold dimness, the atmosphere moves with extraordinary speed. Neptune demonstrates again that the outer solar system is not a realm of stillness. It is a realm where hidden energy often matters more than visible illumination. The planet's magnetic field adds another layer of surprise. As with Uranus, Voyager finds that Neptune's magnetic field is significantly tilted relative to the rotation axis and offset from the planet's center. This suggests that the internal region generating the field differs from the simpler deep-core expectation derived from earlier planetary cases. The comparison between Uranus and Neptune becomes especially valuable here. Together, they define the ice giant category, more clearly showing both shared traits and open questions. They are similar in broad class, yet not identical in atmospheric behavior, internal heat release, or visible appearance. Voyager's brief passage cannot settle every question, but it establishes that these distant worlds are not minor variants at the edge of the solar system. They are major planetary types in their own right, with physics that may apply to many similar worlds around other stars. Neptune's ring system is also confirmed and examined in greater detail. Like the rings of Uranus, these are faint and dark compared with Saturn's brilliant display, yet they possess their own distinct structure. Certain segments had earlier appeared brighter in incomplete observations, giving rise to ideas about arcs or clumped regions. Voyager helps clarify the arrangement, showing that the ring system is real subtle and dynamically interesting. Even here at the final giant planet matter is organized into narrow orbital forms shaped by gravity collisions and resonance. The outer planets continue to echo one another while preserving their differences. But it is Triton that gives the Neptune encounter its deepest sense of strangeness. This large moon orbits Neptune in the reverse direction, compared with the planet's rotation, a retrograde path that strongly suggests it did not form alongside Neptune in the ordinary way. Instead, it is widely understood as a captured body, likely originating in the distant outer populations of icy worlds. If that is so, then Triton is not simply a moon. It is an adopted world seized by gravity and transformed by a new orbital history. Voyager's images reveal a pale surface marked by cantaloupe-like textures, smooth plains, dark streaks, and signs of active processes. Most startling are the plume-like features interpreted as geyser activity, likely driven by seasonal sunlight penetrating translucent surface ice and warming darker material beneath. In that weak, distant sunlight on a frozen, captured moon at the edge of the planetary realm, material is still moving. Triton is cold beyond ordinary human imagination, yet it is not inert. Its surface preserves evidence of internal or seasonal change, and its geology appears younger in places than expected for such a remote body. This discovery broadens the lesson already learned from Io and hinted by other moons. Activity in the solar system does not belong only to warm worlds. It can emerge from tidal stress, from internal heat, from chemical properties of ice, or from subtle seasonal energy acting over long times. Triton becomes one of the great final gifts of the Grand Tour because it reveals geological vitality where stillness seems most likely. The Neptune encounter also carries a strong sense of finality. After this passage, there are no more giant planets ahead, no next orbital transfer waiting to reshape the mission into another close flyby. Voyager 2's planetary tour ends here. The Grand Tour, first imagined decades earlier through calculations of alignment and gravity assist, has reached its last world. Yet the ending is not narrow. Neptune and Triton ensure that the final encounter enlarges the scientific horizon rather than simply closing it. The blue planet shows fierce winds, deep weather, and unusual magnetism. The captured moon shows that frozen surfaces can remain active and that the history of the outer solar system includes movement capture and transformation on scales far beyond ordinary planetary formation stories. When Voyager leaves Neptune behind, it does so having completed the most extensive direct reconnaissance of the outer giant planets ever achieved. The mission has moved from Jupiter's turbulence to Saturn's rings, through Uranus's tilted quiet, and on to Neptune's dynamic blue distance. At the very edge of this planetary sequence, Triton turns the final glance outward into one more act of surprise. The last giant before the boundary is not silent. It sends the spacecraft onward with one final reminder that remoteness does not mean simplicity, and that the outer solar system still holds motion, weather, and change even in its farthest cold. After Neptune, the outward journey enters a region that seems at first glance to offer very little. The giant planets are behind the spacecraft, their rings and moons no longer filling the cameras with structure and contrast. The sunlight continues to weaken. Familiar landmarks fall away. What remains appears to be a widening dark, a stretch of distance so immense that ordinary imagination tends to flatten it into emptiness. Yet this outer realm is not empty, and one of Voyager's lasting contributions is to show that the space beyond the planets still possesses organization, pressure, motion, and scientific meaning. The solar system does not end when the last major planet is passed. It extends outward through zones shaped less by visible worlds than by fields, particles, and sparse populations of icy bodies. In this sense, the departure from the planetary region is not a departure from structure. It is a transition from one kind of structure to another. The earlier mission has been guided by close encounters, by worlds that announce themselves through reflected light and gravitational pull. Now the mission enters a domain where the most important boundaries are nearly invisible, and must be sensed through instruments rather than seen. Beyond Neptune lies a broad region inhabited by small frozen bodies, leftovers from the history of planetary formation and long-term gravitational evolution. Some orbit in the Kuiper Belt, a vast population of icy objects distributed beyond the orbit of Neptune. Others follow more scattered or elongated paths, shaped by interactions with the giant planets over immense spans of time. Voyager does not pass close to most of these bodies, and it does not become a dedicated explorer of that population in the way later missions do. Still, the spacecraft travels through the larger realm that contains them, and their existence matters because they remind science that the outer solar system is not a clean edge, but a layered continuation. The Sun's family includes much more than the 8 major planets. It also includes dwarf planets, ice remnants, dust and distant reservoirs of material extending far outward. Yet even these populations do not define the deepest significance of Voyager's later journey. The most important transition ahead is not from one orbiting object to another. It is from the inner regions dominated strongly by solar outflow toward the far boundary where that influence weakens against the interstellar medium. In the space beyond the planets, the solar wind still flows, though its density continues to drop as it spreads outward. Magnetic fields carried by that wind remain present. Energetic particles continue to move through the region. This means that the spacecraft is still traveling inside the Sun's great bubble, though now it is moving through parts of that bubble never before sampled directly. The absence of planets makes the space seem simple, but it actually becomes scientifically subtler. Near the planets, comparison is often immediate. One can look at clouds, rings, moons, and magnetic effects around a visible body. Here the phenomena are diffuse. They are known through counts of particles shifts in field direction, plasma waves, and changes in radiation intensity. The language of exploration becomes quieter, yet not less profound. Instead of asking what a world looks like, the mission begins asking what the medium itself is doing. The outer solar system in this phase is shaped by immense scale. Signals take many hours to cross the distance between spacecraft and Earth. Commands must be planned long before their effects can be known. The old idea of piloting gives way entirely to the discipline of patient listening. This remoteness also changes the emotional meaning of the mission. During the planetary era, each encounter has a dramatic date, a peak of images, a clear moment of arrival. Beyond the planets, there is no single new globe waiting ahead. The discoveries come slowly, often encoded in trends rather than pictures. The mission becomes one of persistence rather than spectacle. That shift is part of why Voyager's later achievements carry a different kind of grandeur. They require a long attention span, both technical and human. There is also another sense in which this region remains populated. Light from the Sun, though weak, still extends outward. The gravitational influence of the Sun reaches vastly farther than the planetary zone. Comets on long-period orbits may take thousands or even millions of years to complete their paths while still remaining bound to the Sun. Far beyond Voyager's route, there may lie the remote cloud of icy bodies thought to supply many such comets, though that distant reservoir remains more theoretical than directly observed as a coherent structure. The solar system, then, is not ending in any simple way as Voyager moves on. It is thinning, opening, and changing character. Dense local systems give way to a sparse field of matter and influence. The journey becomes less about destinations and more about gradients. The spacecraft is approaching a frontier defined by slowing solar wind, changing particle populations, and the eventual negotiation between solar and interstellar pressures. This frontier cannot be mapped in advance with complete confidence because it breathes and shifts over time. It responds to the solar cycle, to variations in outflow, and to the conditions of the medium outside. In this way, the seemingly empty space beyond the planets becomes the stage for one of the most important boundary studies in all of space science. Voyager is no longer merely a traveler leaving home. It is becoming a probe of the home's outer skin. The great planetary worlds remain essential to the mission's fame, but here the deeper transformation begins. The spacecraft passes beyond the last giant and enters an extended borderland where the sun is still present yet less absolute. The known architecture of orbits gives way to the hidden architecture of plasma and pressure. Darkness increases, but so does scientific sensitivity. The farther Voyager goes, the less useful ordinary visual intuition becomes, and the more important it is to understand the solar system as a moving physical system embedded in the galaxy. Beyond the planets lies not emptiness, but preparation. It is the long, quiet approach to the region where the solar wind begins to yield, where the outward breath of the sun meets mounting resistance, and where the meaning of the mission begins to turn from exploration of distant worlds to exploration of the boundary that surrounds them all. Far beyond the orbit of the outer planets, the solar wind continues to stream away from the sun, carrying charged particles and magnetic field lines into the dark. For a very long distance, this outflow remains dominant, even though it steadily thins as it spreads across a larger and larger sphere. But no outward flow can expand unchanged forever. At some point, the pressure of the surrounding interstellar medium becomes strong enough to matter decisively, and the solar wind begins to lose the easy command it once held closer to the sun. One of the first great signs of this transition is a region called the termination shock. The name suggests a sudden ending, though the reality is more physical and more subtle. It is the place where the solar wind, moving faster than the local speed of sound in the plasma through which it travels, slows abruptly to a subsonic flow because of the pressure building from outside. A shock in this context is not an emotional word or even an ordinary collision. It is a boundary across which properties such as speed, density, temperature, and pressure change rapidly. In the vastness of space, this is one of the ways invisible fluids announce that they have reached a new condition. Before the termination shock, the solar wind moves outward in a supersonic state. After the shock, it is slower, hotter, and more compressed. This transformation matters because it marks the beginning of the outer boundary region in a more active sense. The sun's influence continues beyond the shock, but it no longer expands with the same freedom. The flow has begun to yield. For years before Voyager reaches this region, scientists can only model where the termination shock might lie. Estimates vary because the answer depends on changing solar conditions and on the external pressure exerted by the interstellar medium. A stronger solar wind can push the shock farther out. Weaker solar activity can allow it to move inward. This means there is no perfectly fixed distance at which it must appear. It is a living boundary responsive to long-term changes carried outward from the sun. That uncertainty makes direct measurement especially valuable. Voyager is not traveling toward a line painted in space. It is traveling toward a condition that must be inferred from changes in particle behavior, plasma properties, and energetic radiation. When Voyager 1 reaches the termination shock, the evidence comes through a combination of instrument readings, that together show a major shift in the character of the surrounding plasma. Voyager 2 later encounters the shock at a different distance, an important result because it confirms that the heliosphere is not perfectly symmetrical. The two spacecraft are moving in different directions, and the fact that they cross the shock at different distances suggests that the Sun's outer bubble is shaped by uneven forces. The interstellar magnetic field, the Sun's own variability, and the direction of motion through the local interstellar medium all appear to play a role. The boundary is therefore not a neat sphere. It is compressed in some regions and extended in others, more like a changing three-dimensional form than a geometric shell. The termination shock also matters for energetic particles. Shocks in space can accelerate particles, increasing their energy through repeated interactions with turbulent magnetic structures. This means the region is not only a passive boundary where the solar wind slows. It is also an active physical site where particles can be redistributed and energized. Voyager detects changes in particle populations that help reveal this role. Some lower energy particles of solar origin behave differently across the boundary. Galactic cosmic rays begin to show a rising importance as the Sun's shielding influence weakens. The shock is therefore part of a larger transformation in the radiation environment as well as in the plasma flow. It is one of the first places where the mission's language shifts decisively away from planets and toward pure space physics. There is no surface to image here, no rings to resolve, no moon to map. The discovery is made through patterns in invisible matter. Yet this does not make it less dramatic. In some ways, it makes it more profound, because the spacecraft is revealing the behavior of the Sun's outermost breadth, the place where stellar outflow begins to bow to galactic surroundings. The word termination can be misleading, because the Sun's influence does not end here. The solar wind continues past the shock, but in altered form. The region beyond remains within the heliosphere, still shaped by the Sun's still carrying solar material and magnetic structure. What has changed is the balance of forces and the character of the flow. The solar wind has crossed from free expansion into a more crowded, pressured state. In human terms, it is as though a great river moving across an open plain has entered shallower ground and begun to slow and pile up. The analogy is imperfect because plasma in space is not water, yet it helps suggest why the termination shock is less a wall than a regime change. Voyager's crossing of this boundary is one of the mission's most important steps, because it demonstrates that the outer solar system is structured not simply by distance, but by dynamic transitions in the flow of matter. The spacecraft has left the planetary realm behind and reached a place where the Sun's extended atmosphere begins to transform under external pressure. The mission that once captured volcanoes on Io and storms on Neptune is now measuring the changing state of a stellar wind at the edge of its dominance. The shift is immense in meaning. It reveals that the solar system is surrounded not by an empty fade into nothing, but by organized plasma boundaries through which the Sun negotiates with the galaxy. At the termination shock, that negotiation becomes unmistakable. The outward wind is no longer racing freely into the dark. It has begun to slow compress and change, and Voyager is there to hear the first clear sign of that yielding. Beyond the termination shock lies a region that is neither the fully free solar wind of the inner heliosphere, nor the true interstellar medium beyond the Sun's reach. It is an in-between domain, a broad and unsettled borderland, where the solar wind has already slowed, but has not yet given way completely. This region is called the heliosheath. The name suggests a sheath or wrapping around the heliosphere, and, in a general sense, That image is useful, though the reality is not smooth or uniform. The heliosheath is a place of compression, turbulence, redirected flow, and gradual transition. Here, the outward moving plasma from the Sun becomes hotter, denser, and more complicated in behavior as it responds to the pressure of the interstellar medium outside. If the termination shock marks the first abrupt yielding of the solar wind, then the heliosheath is the long, restless consequence of that yielding. It is the region where the Sun's influence remains present, but no longer simple, where the solar wind is still solar in origin, yet no longer free in motion. Before Voyager enters this domain, scientists can imagine it only through models and indirect inference. They expect it to be disturbed, but the degree and pattern of that disturbance remain uncertain. Once the spacecraft begins sampling it directly, the heliosheath proves to be less like a clean layer and more like a dynamic zone with shifting structures and uneven behavior. The solar wind that has passed through the termination shock now moves more slowly and with greater internal disorder. Magnetic fields become compressed and folded. Charged particles do not merely stream outward in a simple radial line. They scatter, drift, and respond to changing local conditions. In some regions, the plasma appears more turbulent than expected. In others, changes unfold gradually, rather than in the sharply separated manner earlier simplified pictures might suggest. This makes the heliosheath scientifically rich, because it is not just a border to be crossed. It is a laboratory for understanding how a star's outflow behaves when confronted by the wider medium between stars. One of the reasons the heliosheath matters so much is that it is intimately tied to the way energetic particles move through the solar system. The Sun emits energetic particles during eruptions, while the galaxy supplies cosmic rays accelerated by powerful astrophysical events far beyond the solar system. The heliosheath acts as a modulation region between these populations. As Voyager travels through it, changes in particle counts help show how the Sun's shielding influence weakens. Certain particles associated with the inner heliosphere decline. Galactic cosmic rays become more prominent. Yet these shifts do not always happen in smooth or expected patterns. The heliosheath contains magnetic structure and moving disturbances that can trap, deflect, or channel particles in ways more intricate than early models assume. This is one reason the region comes to seem less like a passive shell and more like a living boundary environment. The word living here does not mean biological. It means variable, responsive, and full of internal process. The heliosheath also reveals that the heliosphere has thickness. The edge of the Sun's domain is not a single instant of transition. It occupies distance. A spacecraft can spend years moving through it. That fact alone changes how the outer solar system is imagined. The frontier is not a knife-edge line, but an extended zone of negotiation. The Sun's outward pressure is being redistributed and diminished there, while the interstellar medium applies opposing pressure from outside. The result is a compressed and heated plasma region whose properties depend on solar activity, large-scale magnetic geometry, and local conditions in interstellar space. Voyager 1 and Voyager 2 cross this borderland in different directions and at different times, allowing scientists to compare two paths through the Sun's outer skin. Those comparisons become important because they show that the heliosheath is not identical everywhere. It varies with latitude, direction, and time. This supports the growing understanding that the heliosphere is asymmetrical and temporally variable rather than perfectly balanced and fixed. Within the heliosheath, the magnetic field carried out from the Sun can become draped and intensified. This draping is part of what happens when outward flow slows and interacts with external pressure. At the same time, disturbances from solar activity that began much closer to the Sun may still propagate outward and influence local conditions. In this sense, the heliosheath is a place where events separated by enormous distances remain linked. A change in solar output can much later alter the far boundary environment through which Voyager is traveling. That long causal chain is one of the quiet wonders of heliophysics. The Sun and its boundary are connected across spans so large that human intuition struggles to hold them together. Yet the instruments aboard a small spacecraft can trace the relationship. Another striking aspect of the heliosheath is that it becomes a region where expectations about neat boundaries repeatedly have to be adjusted. Scientists seek signs of the final crossing into interstellar space, but the data often present ambiguity. Some indicators suggest approach, then partial retreat. Some particle populations change before others. Magnetic behavior proves especially important, yet not always in the simplest way anticipated. The heliosheath therefore becomes a zone of patience as much as discovery. Mission teams must interpret gradual shifts, temporary anomalies, and layered evidence. The frontier does not announce itself all at once. It must be understood through persistence. This period in the Voyager story is less visually famous than the planetary flybys, but in scientific terms, it is among the deepest. The spacecraft is now exploring the outer architecture of the heliosphere itself, turning the idea of the solar system from a collection of worlds into a structured interaction between star and galaxy. In the heliosheath, the Sun's breath has slowed. It is warmer, denser, and more crowded than before. It no longer flows outward with the same simple confidence. It bends under pressure, stores energy in magnetic distortions, and mediates the approach of galactic particles. This makes the region feel both like an ending and a preparation. It is still within the Sun's extended domain, yet already touched by what lies beyond. The heliosheath is therefore the long threshold before the final boundary, a turbulent wrapping where the solar wind gathers itself, weakens, and slowly approaches the point at which the medium between stars will at last begin to dominate. Beyond the heliosheath lies the boundary that has long carried a special weight in the Voyager story, the place where the Sun's outward influence ceases to dominate in the same way, and the interstellar medium begins to assert itself more fully. This boundary is called the Heliopause. It is often described as the edge of the heliosphere, though even that phrase can mislead if it suggests a clean, motionless wall. The heliopause is better understood as a contact boundary between two plasma domains. On one side lies solar material that has streamed outward from the Sun and been slowed, heated, and compressed through the outer heliosphere. On the other side lies the local interstellar medium, the sparse gas and magnetic field of the galaxy through which the Sun is moving. At the heliopause, these two domains meet. They do not simply mix without structure, and they do not remain perfectly isolated in a rigid geometric sense. Instead, they form a shifting frontier defined by pressure balance, magnetic behavior, and changes in particle populations. For decades, this boundary is a concept built from theory and indirect evidence. With Voyager, it becomes a place sampled by instruments, though even then it does not reveal itself in the simple manner many expect. One reason the crossing is so scientifically important is that it marks a change in what kind of space the spacecraft is moving through. Inside the heliosphere, even in the distant heliosheath, the plasma environment is still primarily shaped by the Sun. Beyond the heliopause, the surrounding plasma belongs to the interstellar medium. That does not mean the Sun becomes irrelevant in an instant. its gravity still extends far outward, and its light continues through space. But the local plasma conditions, the particles bathing the spacecraft and the large-scale magnetic environment, begin to reflect the galaxy more than the solar wind. This is why the heliopause carries such symbolic force. It is not the edge of the solar system in every possible sense, but it is the edge of the Sun's plasma bubble, and crossing it means entering a new physical medium. When Voyager 1 approaches this boundary, the evidence does not arrive as a single dramatic visual event. There is no visible shoreline, no change in color, no abrupt image of crossing from one domain to another. Instead, there are changes in energetic particle populations, plasma-related measurements, and magnetic conditions. One of the clearest signs is the sharp decline in lower-energy charged particles associated with the heliosphere, accompanied by a pronounced rise in galactic cosmic rays. This indicates that the Sun's shielding influence has dropped and that the spacecraft is now in a region where interstellar particles have greater access. For many scientists, this is one of the strongest signatures that the crossing has occurred. Yet interpretation is not immediate in every respect, because some expected markers do not behave exactly as predicted. In particular, the direction of the magnetic field does not shift as dramatically as some early simple models suggest it might. This creates a period of uncertainty and debate. The data imply that Voyager 1 has entered interstellar space, but the details force a refinement of what that transition should look like. It becomes clear that the interstellar magnetic field near the boundary may be draped in a way that preserves a direction more similar to the solar field than many had anticipated, or that the local geometry is more subtle than earlier simplified pictures allow. This is one of the important lessons of the crossing. The heliopause is real, but it does not exist to satisfy neat expectations. It exists as a physical consequence of plasma interaction, and nature is under no obligation to make that interaction visually or conceptually tidy. Voyager 2 later crosses the heliopause as well, and because it carries a functioning plasma instrument able to provide direct measurements that are especially valuable, its crossing helps confirm and clarify the picture. It does so at a different distance from the Sun than Voyager 1, reinforcing the conclusion that the heliosphere is not symmetrical and that the boundary shifts with direction and solar conditions. The two crossings together become much more powerful than either one alone. They show that the heliopause is neither fixed nor uniform. It moves, it breathes, and it responds to changes. It is shaped by the Sun's activity over time and by the pressure and magnetic structure of the interstellar medium outside. The boundary therefore behaves less like a static shell and more like the skin of a moving variable bubble traveling through a larger environment. The scientific value of crossing the heliopause extends beyond the fact of entering interstellar space. It also reveals how a star interacts with the galaxy on large scales. The Sun is not unique in producing an outflow. Other stars also generate stellar winds and carve cavities into surrounding space. By studying the heliopause directly, Voyager offers insight into a general astrophysical process that may occur around many stars throughout the Milky Way. This gives the mission a broader meaning. The spacecraft is not only exploring the outskirts of one solar system, it is helping explain how stellar systems define and defend their local environments against the medium between the stars. There is also a human dimension to the crossing that is quiet but profound. A machine launched in the 1970s, built with modest memory and enduring power from decaying radioactive heat, continues long enough to pass beyond the boundary of the Sun's plasma bubble and send evidence of that passage home. The event is separated from its cause by decades of travel, by generations of engineers, and by distances so large that signals need many hours to return. Yet the connection holds. Commands are sent, data are received, and interpretation unfolds. At the Heliopause, the mission's identity changes once again. It is no longer merely a traveler in the far reaches of the heliosphere. It becomes a direct sampler of the interstellar medium just beyond the Sun's protective bubble. The crossing is not a simple line in space, but a transition of conditions, subtle in detail and immense in meaning. It is the point where the outward breath of the Sun gives way to the wider sea through which the Sun itself is moving, and where Voyager at last begins to drift not only beyond the planets and not only beyond the heliosheath, but into the medium between the stars. Once Voyager reaches the boundary of the heliosphere and begins sampling the medium beyond it, one of the most important outcomes is not simply confirmation that the spacecraft has crossed into interstellar space, but the recognition that many long-held expectations about that frontier require revision. The outer edge of the Sun's domain proves to be more complex, less symmetrical, and more dynamic than earlier simplified pictures suggest. Over time, the two spacecraft help reveal a set of especially important findings that reshape understanding of the heliosphere, the heliopause, and the nearby interstellar medium. These findings are often discussed separately in technical literature, but together they form a broader lesson. The boundary between the Sun and the galaxy is not a neat shell surrounding a static system. It is an active, uneven, evolving interface shaped by magnetic fields, particle pressures, and time-dependent solar behavior. One major discovery is that the heliosphere is asymmetrical. Voyager 1 and Voyager 2 do not encounter the major outer boundaries at the same distances from the Sun. The termination shock occurs farther out along one path than along the other, and the heliopause crossing also happens at different distances. This means the heliosphere is not a simple sphere centered evenly around the Sun. Its shape is distorted lightly by the direction and strength of the interstellar magnetic field, by the Sun's motion through the local medium, and by internal solar variations that propagate outward over long times. This asymmetry matters because it changes the conceptual model of the Sun's protective bubble. Instead of a smooth geometric form, the heliosphere appears as a structure with compression in some directions, extension in others, and ongoing time variability superimposed on the whole shape. A second important discovery involves the magnetic field at the heliopause. Many early expectations assume that once the spacecraft crosses into interstellar space, the local magnetic field direction will show a dramatic and unmistakable turn compared with the field carried outward from the Sun. But Voyager 1's measurements complicate that expectation. The field direction does not shift as sharply as some had predicted, even though particle evidence strongly suggests that the spacecraft has crossed the boundary. This initially produces uncertainty, but later interpretation points toward a more subtle reality in which the interstellar magnetic field near the heliopause may be draped or aligned in a way that reduces the directional contrast. The discovery is important because it shows that magnetic geometry at the boundary cannot be treated as a simple before and after picture. The field is structured by interaction, and the transition between solar and interstellar domains preserves more continuity than some simplified models assume. A third major finding concerns the density of plasma beyond the heliopause. Direct plasma measurements are limited in different ways on the two spacecraft, yet Voyager 1 is able to infer the density of the surrounding medium through the detection of plasma oscillations triggered by shocks propagating outward from solar activity. These oscillations indicate that the plasma density outside the heliopause is substantially higher than inside the heliosheath, consistent with the expectation that the spacecraft has entered interstellar space. This is one of the elegant aspects of the mission. Even when an instrument does not operate in the most direct possible way, nature provides another route. A disturbance from the Sun travels outward, excites oscillations in the local plasma, and those oscillations reveal the density of the medium around the spacecraft. The result confirms that the crossing is not merely a change in particle counts, but a movement into a genuinely different physical environment. A fourth discovery involves cosmic rays. As Voyager approaches and then crosses the Heliopause galactic cosmic ray, intensity rises, while certain lower energy particles associated with the heliosphere decline sharply. This demonstrates how strongly the heliosphere modulates incoming radiation from the galaxy. It is not an absolute shield, but it is a meaningful one. The result matters not only for understanding the outer solar system, but also for broader questions of radiation exposure in space and the role of stellar winds in shaping habitable environments around stars. A fifth finding is that the heliopause itself is not still. Evidence suggests that it moves in response to solar conditions expanding and contracting as the strength of the solar wind changes over the solar cycle and as disturbances propagate outward. This turns the boundary into a breathing interface rather than a permanent fixed location. A spacecraft may approach a condition encounter local changes and reveal that the frontier has thickness and motion rather than remaining fixed like a wall. A sixth important result is that the heliosheath and heliopause region are more structured and variable than early broad models imply. Instead of a clean progression through simple layers, the data show abrupt shifts, periods of ambiguity and local complexity in particle behavior and magnetic configuration. This means that the Sun's interaction with the galaxy produces not just a boundary, but a textured zone of negotiation. A seventh discovery, broader than any single measurement, is that direct exploration of the heliosphere's edge changes the understanding of stellar astrospheres in general. The Sun's bubble becomes a nearby example of a phenomenon that likely surrounds many other stars. By learning that the boundary is asymmetric, magnetically subtle, time-dependent and important for cosmic ray shielding, scientists gain insight into how stars interact with surrounding interstellar matter throughout the galaxy. Together, these findings alter the meaning of the mission's final phase. Voyager is no longer simply the spacecraft that visited the giant planets. It becomes the source of a revised physical picture of the Sun's frontier. The heliosphere is not a static container. The heliopause is not a crisp universal line. The interstellar magnetic field does not announce itself in the simplest possible way. The cosmic ray environment changes profoundly across the boundary. Plasma density rises more sharply than the eye could ever witness, and the entire system turns out to be shaped by motion, asymmetry, and time. What makes these findings especially striking is that they emerge from instruments built in the 1970s, operating far beyond their planned lifetime, still sending faint data home across distances measured in billions of miles. The discoveries are surprising, not because nature behaves irrationally, but because simplified human expectations yield to more intricate reality. At the edge of the heliosphere, theory is not overturned so much as deepened. The boundary exists, but it is richer than anticipated. The Sun's frontier is active, uneven, and alive with structure, and Voyager's long outward drift reveals that the space between star and galaxy is not a simple separation. It is a place where forces overlap, where shielding weakens, where fields bend, and where the physical reality of a stellar bubble becomes far more subtle than the old diagrams suggest. Beyond the heliopause, the meaning of Voyager changes once again. The spacecraft is no longer traveling through the Sun's outer boundary region alone. It is now sampling the local interstellar medium itself, the sparse matter and magnetic environment that occupies the space between stars in this part of the galaxy. This medium is thin beyond ordinary intuition, yet it is not negligible. It has density, temperature, pressure, field structure, and particle populations, and each of these properties helps define the wider environment through which the Sun moves. For most of scientific history, this medium is studied indirectly through observations of starlight radio signals and theoretical modeling. Now, Voyager offers something rare, direct in situ measurement. The spacecraft does not enter a dramatic new visual landscape. There are no bright structures surrounding it, no nearby star, no illuminated cloud. Instead, the transition is known through the behavior of particles and plasma. This is fitting because the interstellar medium in this local region is more a physical state than a visible scene. Yet that state carries deep significance. It is the material from which stars are born, through which stellar systems travel, and within which magnetic and radiative processes unfold across the galaxy. One of the most important quantities Voyager helps determine is plasma density. In the heliosheath, the density of the surrounding plasma is relatively low. Once beyond the heliopause, measurements and inferred plasma oscillations indicate a distinctly higher density consistent with conditions expected in the local interstellar medium. This increase matters not because the medium becomes dense in any ordinary human sense, but because it marks a clear environmental change. A spacecraft that once drifted through plasma dominated by solar outflow now finds itself in plasma associated with the galaxy. The difference is subtle in absolute terms and profound in physical meaning. It confirms that the spacecraft is no longer in a region where the Sun's wind sets the local plasma character. Instead, it is embedded in material shaped by the broader interstellar environment. Pressure in this medium is also revealing. Pressure here is not just one thing. It includes contributions from thermal motion, from magnetic fields, and from energetic particles. The balance among these forms helps determine how the heliosphere is shaped and how it responds to the surrounding galaxy. Voyager's measurements contribute to that balance by clarifying the conditions just outside the heliopause. The local interstellar medium exerts enough pressure to slow compress and confine the solar wind, and the details of that pressure help explain why the heliosphere has the size and asymmetry that it does. This turns the medium beyond the Sun's bubble into more than a passive backdrop. It becomes an active shaper of the solar system's outer form. Temperature in the interstellar medium can also be deceptive if judged by ordinary experience. The local plasma may be considered warm in scientific terms because the particles possess substantial kinetic energy, yet the density is so low that the total heat content per volume remains extremely small. This is one of the counterintuitive realities of space physics. A medium can be warm in terms of particle motion and still contain almost no matter. Voyager does not feel heat as a living being would, but its instruments can register the physical conditions that define such a state. The local interstellar medium thus emerges as a realm where common language must be translated carefully into plasma terms. Warm does not mean fiery. Dense does not mean crowded. Even pressure, though physically real, acts through tiny values sustained over immense distances. Magnetic structure is another crucial part of the environment. The field beyond the heliopause is faint, yet it guides the motion of charged particles, and helps shape the interaction between the heliosphere and interstellar space. Voyager's measurements suggest that the local interstellar magnetic field near the boundary is not arranged in the simplest way once imagined. Its geometry, strength, and draping behavior all influence how the heliopause forms and how cosmic rays enter the solar system. This is one reason the post-crossing data remains scientifically valuable year after year. The spacecraft is moving through a medium where magnetic behavior influences almost every other measured property. It is not simply floating through neutral emptiness. It is moving through a magnetized plasma with structure and consequence. Cosmic rays remain an especially important part of the picture. Beyond the heliopause, Voyager detects a radiation environment in which galactic cosmic rays are more prominent than they are deeper inside the heliosphere. This provides direct evidence of the heliosphere's shielding role and helps map the gradient between solar-dominated and galactic-dominated particle conditions. The local interstellar medium is therefore not only matter and field. It is also a radiation environment carrying energetic particles from distant astrophysical events across the galaxy. By measuring this environment directly, Voyager contributes to understanding how such particles propagate and how stellar bubbles like the heliosphere modulate their access to planetary systems. There is a quiet grandeur in this phase of the mission. No new planet appears. No moon rises into frame. The measurements come as streams of numbers, as variations in counts and oscillations and field strengths. Yet, in those numbers, lies a direct human contact with the medium between stars. The spacecraft built for a grand planetary tour becomes an instrument of galactic neighborhood science. It tells not only where the sun's domain weakens, but what lies immediately beyond it. It reveals that the interstellar medium is not an abstraction left to distant spectroscopy. It is a measurable local environment with physical properties that can be sampled directly by a machine carrying the legacy of a much earlier age of engineering. This gives the mission a remarkable continuity. The same project that once revealed active volcanoes on Io and strange terrains on Triton now measures plasma density, magnetic geometry, and cosmic ray intensity in interstellar space. The scale of the transformation is immense, yet the instrument platform is the same. Voyager continues drifting farther into the local interstellar medium, and with every additional measurement, it deepens the sense that the galaxy is not made only of stars and large luminous events. It is also made of the thin, persistent medium between them, the material that fills the space no telescope can easily make dramatic, yet which shapes the boundaries of stellar systems and carries the conditions of the wider Milky Way. In this region, Voyager is no longer merely beyond the planets. It is within the galaxy in a more immediate physical sense, sampling the quiet substance through which stars travel and against which the sun must continually press. Far beyond the last planetary encounter and beyond the heliopause, Voyager continues on a path that no human mission had ever followed before it. Not because it is racing toward a destination soon to be reached, but because it endures. Its movement through interstellar space is steady, silent, and measured on scales that far exceed a human lifetime. The spacecraft is still bound to the sun by gravity and will remain so for an immense span of time. Yet, in another sense, it has already entered a wider galactic context. It is no longer defined mainly by the planets it once visited. It has become a drifting witness, carrying outward both scientific instruments and one of the most deliberate symbolic objects ever placed aboard a machine, the Golden Record. This record is not designed as a practical communication device in the ordinary sense. It is not broadcasting, not searching, not expecting reply. It is a message prepared as an act of representation, a curated expression of life and culture from Earth attached to a spacecraft whose primary mission is scientific. The presence of the record gives Voyager a dual legacy. It is at once an instrument of measurement and a vessel of memory. The record carries sounds, music images encoded for reconstruction, and basic information intended to show something of Earth's life languages and place in the cosmos. Its inclusion reflects a rare decision in space exploration. Alongside the discipline of data collection, there is room for symbolic meaning for the idea that a machine leaving the familiar domain of the planets might also bear a trace of the beings who sent it. The record does not change the physics of the mission, but it changes the imagination around it. It turns the spacecraft into more than a probe. It becomes a time capsule set adrift on an interstellar path. The likelihood that any distant intelligence will ever find and decode it is extraordinarily small, and the mission's scientific value does not depend on that possibility. Yet the record remains powerful because it expresses how humanity chooses to think about its own outward reach. It suggests that exploration is not only the acquisition of knowledge, but also the framing of identity. To send a spacecraft beyond the edge of the heliosphere and attach to it a distilled portrait of Earth is to acknowledge that science and meaning are often intertwined. Voyager's future motion is equally striking when measured on deep time scales. Over tens of thousands of years, the spacecraft will pass at great distance from other stars, though not in the sense of arrival or encounter familiar from fiction. Interstellar space is too vast for that. Even at its great speed, Voyager moves through a galaxy where the average separation between stars makes close approach an event of distant ages rather than mission planning. It will not enter another planetary system in any practical exploratory sense. It will drift, carrying diminishing energy, aging hardware, and a record of the civilization that launched it. Its power source continues to decline, and this imposes the final finite horizon on the active mission. Instruments have already been turned off over time to preserve energy, and more will inevitably follow. Eventually, the spacecraft will fall silent, not because it has stopped moving, but because it will no longer have the power to transmit. That future silence gives the mission a poignant structure. Scientifically, Voyager is most valuable while it can still send measurements home. Symbolically, it remains significant even after silence, because the craft itself continues onward as an artifact of exploration. In that later state, it will become a true derelict in the literal sense, not broken in a dramatic event, but simply no longer powered, still intact in the cold, moving through the interstellar medium with no further communication. The scientific legacy of Voyager reaches well beyond the measurements it has already made. It reshapes how scientists understand giant planets, active moon's ring systems, the heliosphere, and the boundary between solar and interstellar space. It also changes the engineering imagination. The mission shows that durable design, modest computational architecture, reliable radio communication, and patient operations can sustain a spacecraft for decades beyond its planned scope. This lesson matters for every later deep space mission. Voyager proves that longevity itself can become a scientific instrument. A spacecraft does not need to be the most advanced in every raw specification if it is built with clarity, resilience, and a mission architecture that can evolve. In this sense, the technology of the 1970s does not survive merely as a relic. It continues to alter modern understanding because it remains active long enough to enter regimes no one expected it to reach at launch. That endurance also reshapes the human story around exploration. Voyager was born in the age of the grand planetary tour, But it lives into an era that can look back across nearly the entire history of modern planetary science and still find it relevant. Generations change, institutions evolve, computers transform. Yet the faint signal from the spacecraft continues for as long as power allows, joining different eras of science through one continuous line of measurement. There is also the lingering influence of the image often associated with Voyager's broader cultural meaning, the pale blue dot view of Earth. Though captured by Voyager 1 before its cameras were later turned off, that image becomes part of the mission's enduring legacy because it reframes the outward journey inwardly. The farther the spacecraft goes, the more clearly Earth appears not as the center of the scene, but as a tiny point within a vast surrounding darkness. This does not diminish Earth, it clarifies its fragility and rarity. The journey outward becomes a way of seeing home more clearly. In that sense, Voyager's final legacy is not only interstellar, it is reflective. It links the exploration of distant space with a more precise awareness of the small inhabited world from which the mission began. Long after its instruments fall silent, Voyager will continue moving through the galaxy as a physical remnant of curiosity, discipline, and care. It will carry its golden record into times beyond any present nation, beyond present language, beyond the continuity of current institutions. Its scientific work will remain in the data already sent home. Its symbolic work will remain in the fact that such a mission was imagined and built at all. The spacecraft from the 1970s does more than survive. It changes the scale on which human beings think about exploration, not by promising arrival at another world, but by proving that patient machinery can cross the frontier of the sun's domain and continue into the deep time of the galaxy, bearing both measurement and memory into the dark. The long motion of Voyager now settles into a quieter scale, where distance is no longer measured by the passing of planets, but by the slow fading of signal and the widening calm of interstellar space. The spacecraft continues outward through a region too thin to see and too vast to hold in ordinary thought, carrying the last active trace of a mission that begins with rare planetary alignment and grows into a study of the sun's farthest boundary. Its path crosses giant worlds, rings storms, moons of ice and fire, the slowing of the solar wind, the turbulence of the heliosheath, and the subtle crossing into the medium between stars. At every stage, the journey reveals that the outer darkness is never empty. It is structured by pressure-light magnetism particles and time. The old machines endure long enough to show that a spacecraft built in one era can continue speaking into another, and that even a faint signal can enlarge human understanding. Far behind them, Earth remains a small and quiet world, circling an ordinary star, while far ahead, the galaxy opens without urgency and without end. In that stillness, Voyager drifts on, carrying the record of a species that learns to measure the dark with patience and to meet immensity not with noise, but with listening.